So let's begin with part 2 of our first video. So here's our calculation. I think I've got my pens working this time. Here's our calculation to calculate the average atomic mass. So if you guys look on your periodic table, you'll notice that most of the atomic masses have decimal places. Which doesn't necessarily mean that you can have like 0.68 of a proton. It just means that the mass that's calculated there is as average. So how do we calculate this average? How do we figure all this out? Well, we look for some of this data here. So if we look at example number 1, lithium actually exists as 2 isotopes. So we have lithium-6, and 7.42% of all the lithium on Earth is lithium-6. There's also lithium-7 that has an extra neutron, and 92.58% of all the lithium on Earth has 7, which means it has 3 protons and 4 neutrons. So to calculate the average weight, we're going to use this formula here. Oh yes, that's a nicer pen. So it's the percent of A times the mass of A divided by 100 plus the percent of B times the mass of B divided by 100 plus and however many I give you. So in this case, I only have 2 different isotopes, so I'm not going to use C because I only really have to do 2. So what I'm going to do is punch in my numbers here. So my percent of A is this, 7.42%, and my mass is 6. So I'm going to put that in. So 7.42% times 6. And I'm going to take that divided by 100. And I'm going to add that to my second isotope, which I'll do in red. So my percent is 92.58, and my mass is 7. So I'm going to write that down. So 92, sorry, point. Let's fix that. 92.58% times 7 divided by 100. So when I punch that all into my calculator, my answer is, I'm going to put it over here just to save room and make sure everybody can see it. So 6.9258, and my symbol was that mu that we talked about in the last video. Now I should round that to the right number of significant digits, which we haven't yet learned in this course. But basically, at least for now, I'll make your rules to the same number of decimal places that are in the question. So in both of my percentages in the question, I had 2 decimal places, so I'm going to round this to 6.93. And if you look on the periodic table, lithium usually has 6.94, so that's pretty close, and that's sort of where we're at. Okay, so let's try magnesium. I will set it up for you. So again, you're going to do the percent, so we'll call this A, we'll call the second one B, and we'll call the third one C in black, and let's see if you can do it. So if you think you know how to do it and calculate the average atomic mass, then go ahead right now. If not, you can keep watching the video and copy it down as I go. So the percent of A in this case is 78.70, and my mass of A is 24. I'm going to divide that by 100. Percent of B is 10.13. I'm going to times that by my mass, which is 25, and divide that by 100. And then C I'll do in black. So C is 11.17% times 26 divided by 100. So you punch all that into your calculator, and your mass should come out to 24.3247. So we're going to round that to 2 decimal places, so 24.32. And your unit is the atomic mass unit, or that mu symbol. So that's how you calculate the average atomic mass. We'll do a couple more examples of that in class. One really kind of cool thing that I wanted to show you was the ratio of protons to neutrons. Have you ever thought of how protons hold themselves together in the nucleus, even though they're all positively charged? So usually we've heard that if we have the same charge, they should actually repel and push off of each other. But this doesn't happen in the nucleus. In fact, the exact opposite happens. The nucleus is really, really hard to break apart. So how do protons overcome this positive repulsion? Well, basically, that's what neutrons do. Because positive charges can be attracted to those neutrons and still hold themselves together. So look at this chart here. So in the first column here, I have their mass, so is the protons plus the neutrons. The last two columns are what I really want you to look at. So look at the number of protons versus the number of neutrons. So look at hydrogen. So hydrogen has one proton, and it can have 0, 1, or 2 neutrons, sorry, depending on which isotope. As you increase the number of protons, so as we go up to say 60 protons, I have a lot more neutrons. So it's not a straight 1-to-1 ratio. I need a lot more neutrons to balance out all those extra positive charges that are now in the nucleus. So that was just one new point I wanted to mention to you. So what do you notice about the number of neutrons and protons for these isotopes? So as your protons increase, your neutrons also have to increase, but they kind of increase by even more. So I kind of represent that with 2 arrows. All right, radioisotopes, our last sort of topic for today. These are isotopes whose nuclei are unstable. So the protons and the neutrons in that nucleus are unstable and actually spontaneously decay or break apart. This releases subatomic particles and energy, and some of that energy can be dangerous. Radioactive isotopes are known simply as radioisotopes, and we're going to talk a little bit more about those in class. But that's, for now, all you need to know about radioisotopes is that the nuclei are unstable and they can break down and form new elements. So the key terms that we learned in the last video and this part 2 were things like the valence electron, a Lewis diagram with all the dots around it, electron pairs and unpaired electrons, and how that can affect the structure of the valence electrons, or the valence shells. We learned a little bit about isotopes and radioisotopes, and I showed you the atomic mass unit and isotopic abundance, or how to calculate the average atomic mass. So if you have any questions about that, make sure you bring them into class.